All right, let's look at lesson 10.7 in your book, page 569, special segments in a circle. I'll start right off with the theorem that says two chords intersecting in a circle. The lengths of the one chord segment multiplied together equal the same calculation in the other chord. What does that mean? Once again, with most theorems, it's easier to see than to read the words. So here is my circle with two chords in it. Chord AC splits into two segments when at the intersection point, AE and EC. The other chord, DB, splits into two segments, DE and EB. So this theorem states that you can take the two segments of each chord, their lengths, and multiply them together, and they will equal the same calculation of the other chord. Let's use that in an example. Supposedly I have, let's given, this circle. All right, and I have a chord and another chord. Looks something like that. And for sake of lettering, we go A, B, and C, D, and my intersection point is point E. Now there's some things I know. I know that that is X long. This is 4, this is 3, and this one is 6. So I now know the 4 segments, and I go back up to my theorem right here, and I can multiply them out. I can take x times 6, or 6x, is equal to 3 times 4, which means 6x is equal to 12. Divide both sides by 6, x is equal to 2. So I know that that value right there is equal to 2 by using this theorem. Let's try that again with a little bit trickier. Let's say I have a road, and on my road I have a tunnel. Looks like that. That's the tunnel. And I know that the tunnel is 12 feet tall, and I know that each side of the tunnel is 24 feet long. Okay? What I'm asked to find out is, this is the part of a circle what is the radius r of that circle? So find r. Well, how do I find r? Well, the first thing I can do is I look at my circle and I say I know I have two chords. This 12 plus the rest of this dotted line, which I'm going to label as x long. Okay? And then I have another chord that is 48 long right here. Well, I know that the segments add up, or can be multiplied together, so 12 times x is equal to 24 times 24. So 12x is equal to 24 times 24. 12x is equal to 576. When I multiply those two together, divide by 12, and I get x is equal to 48. Well, x is equal to 48 is not my r value, it's the dotted line value here. So I now know that D is equal to 12 plus 48, which is equal to 60. R is equal to 1/2 D, which is equal to 30. And that is the radius. All right, let's look at the next theorem in the book. The next theorem is the theorem 1016. And this theorem, 1016, states that if I have two secants and they intersect external to a circle, okay, then I can take the product or the multiplication of the length of the secant, of one secant, times its exterior segment, oops, type that, segment, is equal to the product of the other secant and its exterior segment. What does that mean? Once again, let's take a look at a picture. Here's my circle. And I have a point out here of intersection, and I have two secants. I now have the following points, A, B, C, and D and E. Well, my secant is AC. Its exterior segment is AB. And my other secant is AE, and its exterior segment is AD. So, AC times AB is equal to AE times AD, right there. That is that theorem. The exterior segment is the part of the secant that's outside the circle, multiplied the whole times the length of the whole circle, or the whole secant, equals the same calculation on the other secant. All right. So now that we know that, let's use that one. What is example 3? In example 3, we have the following picture. Here's our circle. We have one secant coming out, exterior, another one coming right across the bottom, and this is point P, point Q, point R, S, and T. All right, now we get the lengths in there. This is 12. This is 2. This is the unknown value, that's R, and inside there is 3. So now we can multiply the parts. The whole is 14 times the exterior is 2 equals the whole, which is 3 plus x, times the exterior, which is x. Okay? So, we multiply that out, we get 28 is equal to 3 times x is 3x, and x times x is x squared. So I just took the x and used the distributive property against 3 plus x. Okay? I now then subtract 28 from both sides. 0 equals 3x. Let's not write that. Let's write it in x squared first, plus 3x. I just rearranged the order of those two, and then I subtracted the 28 from both sides. Now I want to do a factoring table. If you remember your factoring table, I'm going to take two numbers when multiplied together equals negative 28, added together equals the second number, which is positive 3. And factors of 28 are 7 and 4, which are 3 different. So let's try positive 7 times a negative 4. Well, when multiplied together, I get negative 28. When added together, I get a positive 3. So this is my two values inside of my factoring. So there is my factor, x, and I grab my two values, plus 7, minus 4. Now I use the zero product theorem to solve for these two problems. So I said x plus 7 equal to 0. X minus 4 equal to 0. I subtract 7 from both sides. I get x equals negative 7. I subtract 4, or add 4 to each side. The x equals 4. I look at what is my problem. It is the length of this here. So negative 7 is not a valid answer. I cross it out. And this is my answer. All right. Now let's look at the last theorem in this lesson, Theorem 1017. Along the same lines as the first one, this time I have a tangent and a secant. When I have a tangent and a secant that intersect exterior to a circle. Okay, so I've got an intersection of a tangent and a secant exterior to a circle. The square of the tangent equals the secant, the length of the secant, times its exterior segment. And again, let's draw that picture. Here is my circle, here is my tangent line, and here is my secant line. Okay, and let's say WX, Y, and Z. So my tangent is WX squared is equal to my secant, which is WY, times the external segment of my secant, WZ. And that is that theorem. Well, let's use it. Example 4 in your book. Find X, given the following. Here's my circle. I have a tangent line coming off the top. I have a secant right there. Point A is my tangent point of tangency. B, C, and D, and my lengths that I know are 4. This is X, it's the part I'm going to try and find, and this is X plus 2. So once again, I can take my tangent line squared, so it's 4. 4 squared is equal to my complete length of my secant, BD, so that is X plus 2 times X, which is the exterior secant segment. So let's carry that out. 16 is equal to, I'm going to add these together, 2x plus 2 times x. I'm going to do the distributive property, so I get 2x squared plus 2x. I'm going to subtract 16 from both sides. 2x squared plus 2x minus 16. Now I look at this and I can factor divide by 2 on both sides. Dividing by 2 on the 0 side gives me 0 still. But dividing by 2, each of these terms has to be divided by 2. 2x squared divided by 2 just gives me x squared. 2x divided by 2 is x, and negative 16 divided by 2 is negative 8. Now I could factor that. I look for the factoring table. Two numbers multiplied together give me negative 8. Added together give me positive 1. Well, let's try it. Negative 8 and 1 multiplied together, does that give me positive 1? No. How about negative 4 and 2? No. Negative 2 and 4? No. Negative 1 and 8? No. None of them give me the right answer. So this is not factorable. So how else can I solve this? How about the quadratic equation? If you remember that, it is x equals negative b plus or minus square root of b squared minus 4ac all over 2a. So all I have to do is substitute in. What is my a value in this equation? It is 1, the value in front of my squared term. B value in this equation is 1, the value in front of my x term. And my c value is negative 8, the singular number. So now I just have to plug that in. Plus or minus 1 is my b value, plus or minus square root of 1 squared minus 4 times 1 times negative 8 divided by 2 times 1. So I write that all out. I get negative 1 plus or minus 1 minus. A minus and a minus is a plus, so plus 32. 8 times 4 is 32 times 1, all over 2. So once again, I get negative 1 plus or minus square root of 33 all over 2. And I can write that now as two different ways. I can get that as negative 1 plus the square root of 33 all over 2. And x equals negative 1 minus the square root of 33 all over 2. And if I punch that into my calculator, I get approximately, I should write approximately there, excuse me, those are my two equations right there, and I get approximately, punching that into my calculator, 2.37, and over here I get approximately negative 3.37. So now I go back and look at what am I trying to solve. I'm trying to solve this value of x right here, which is a length. So I come back down here to my two lengths that I can choose from, and this one is the negative length, so I don't use it. So this becomes my final answer.